All right, so example 2 says find the chromatic number of the utilities graph from section 5.3. So the chromatic number just means how many colors it takes. So when I did all those examples, for example 1, I just said it was 2 colorable or 3 colorable. That is the chromatic number, okay? So if it takes 2 colors, the chromatic number is 2. If it takes 3 colors, the chromatic number is 3. So if you want to find the chromatic number and see if it's 2, going off of the 2 colorable graph theorem, if you can find any odd circuits, a circuit again goes through the process and goes back to the original, okay? And it doesn't have to use all of the letters. It can be only use 3 of them, okay? But if you can find an odd circuit in a graph, then you cannot use 2 colors. Now we know that this graph is the utility graph, and we know that this graph is not planar. And so there is no guarantee that it's going to take 4 colors. But if you start to go through and you start to look at the circuits, if I start at X, A, Z, now I can't come back here. I have to go either to B or to C. So if I did X, A, Z, B, X, X, A, Z, B, X, that's 4, okay? So that's an even number. If I did X, A, Z, C, Y, B, X. Now I went to all 6, okay? I did 6 vertices. So what ends up happening, now notice when I go back, I don't count the same one over again, okay? So when I'm going, it's how many edges there are. So I count the number of edges, not the number of vertices, because if I go through all 6 of them and come back to the original, some people will say, oh, that's 7. No, that's 6, okay? You count the number of edges that you go on. So this is 1, 2, 3, 4, 5, 6, okay? Or 1, 2, 3, 4. So those are all even circuits. Because none of these are connected, this particular graph is 2 colorable by the 2 colorable graph theorem. And if this is all they're asking for, find the chromatic number. All you have to do is find the chromatic number. You do not have to color anything, okay?